So anything we need to go back over? Modular dispersion mode, chromatic dispersion, material dispersion, multi-mode, stepped index, graded index, single mode. Then we went over to the advantages of each one of them. And we got a single mode fiber. Yes. So these look like they're really big, but what we're doing is we're looking at this right here. This space right here typically is 125 microns from the inside to the outside. So what this is right in the center, this is the core. And then this right here is the cladding. And standard cladding sizes, even though we do have some that vary a little bit, standard cladding sizes is 125 micrometers. So when we look at these conductors, you're looking at about the size of a human hair. You know, that's what we're looking at. So these are our reference cables, and we'll look at that when we look at our power meters. And we have single mode. So single mode, I don't forget what size it is. So if you see yellow or blue, these are single mode cables. Multi-mode cables will usually be orange. And this is the outside jacket. And if you got a sure enough cable that's got multiple conductors on it, it follows basically the same scheme.
So if the single mode, multi-mode use the same connector?
They can, but usually you want to get single mode connectors because the tolerances on single mode connectors are so much better than on multi-mode connectors because the core sizes are so small. So your end alignment is very, very critical on your connectors, right? You understand that, especially on your splices. So this is single mode, and I can't pick this up. I don't think with my camera. Let's try it. Let's take a be interesting to see if it'll work. And then we'll pull this out, and don't spit on it or anything like that because, well, that's not true. We got alcohol wipes that we can clean it with. But I'll see if this thing will pick up. This camera will pick that up. It would be. That way we can record it. And then we'll pull it out and let you actually look at it. Now this is a 200 scope, so this is magnifying by 200 times. We'll see if we can pick it up. It's just too bright. No. This is too bright. The auto adjust on it's not good enough. So y'all have to come up here and look at this. And then we'll use a multi-mode cable. Yeah, very tiny. And in comparison, so that's, I think it's around 9 microns that you're looking at on the actual core. And then this is the, oh my goodness, Rich. I don't see what I did with my end cap. Yeah, and this is, now this needs to be cleaned off, but this is molten oak. We need to clean it. No, this cap that came off now.
Oh, good.
Huh?
On the side of it. How is seeing all the stuff around?
Because it's got a barrel.
So it's looking around the side.
What I want you to realize, this is what we that's what we realize the size. Now, what I want you to notice that the single mode uses a different connector than the multi mode does. That's what some of them we're going to look at. So these, and why I wanted to do that, of course, is to show you. On here, it's not a real good comparison because up here it's real big, right? You understand when we're actually dealing with extremely small conductors. And we actually stopped right here about the buffer, loop buffer, loose tube. Everybody okay there?
Yeah. Well,
Yeah, we're more than halfway through. The different types of cables, and what we'll do is we'll come over here and look at this thing up here. It's actually better than what I have there that we can have, and the different types of names. We don't have any fiber optic ribbon cable, but we do have electrical ribbon cable. Oh, yeah, well, it's ribbon cable, same thing. So fiber optic ribbon cable, you can see how it got its name.
try to make.
So this is ribbon cable.
Yeah. So,
And you can see the each little individual hump would be a conductor. And of course, what's nice about this is that it don't occupy almost no vertical space, but then you can also roll it up and flatten it out and do different types of things. For years, this was the predominant. In fact, this is a hard drive cable right here.
Yeah.
That we used to use on computers before they went to something called serial ATA. The advantage, I'm not even talking about that. So this is ribbon cable. It's not, like I said, we don't have any fiber. Telephone companies usually use a lot of ribbon cable because they're perfectly aligned. And what you can do if you're using a fusion splicer is you can splice a bunch of conductors at the same time. We have a single conductor splicer. But if you looked at fusion splicers, surely one thing that they would show you would be splicing for ribbon cables and also for this. These are just different types of cables. And then we looked at the different problems that we have with our connectors.
So, with the ribbon cable that you use for computers, punch down on one, if you get everything lined right, you basically terminated it. I don't know how many pins are on it. You terminated it every one.
Yeah.
The same thing with fiber.
Well, yeah, but on fiber, on ribbon cable, they usually don't use mechanical splices.
No.
These are usually done with fusion splices. So what you do is once you strip it and do exactly what they want to, then what it does is it actually fuses multiple conductors at the same time.
Okay.
Just like this. So when you terminate
Terminate.
this would you wouldn't terminate with this. This would probably come into some type of a ribbon cable would probably come up to some type of patch panel, and then you go with individual conductors to the individual units, if that makes sense. So usually these cables are what they call premise cables. And these are where we send a bunch of fiber. It's just like the big telephone cable up there that runs on all your power poles. That don't come to your house. So what it does is it constantly goes to these different patch panels and everything, and it brings in, and eventually it breaks it down to two individual wires that actually come into your house. Does that make sense what I'm talking about?
TX and RX?
Huh?
TX and RX?
No, you're talking about transmit and receive, yeah.
Yeah. That's what two individual fibers are.
Fibers are, but bringing it into a building, you don't want to run thousands of individual fibers through a building. So what you do is you run a cable, and then it comes into a patch panel, and then the patch panel breaks it out to individual fibers that would go out to make, yeah. And this technique has been around for years. That's the way a telephone company has done it for years, and that's why you see all these gray boxes all over the place. So in our neighborhood, our telephone lines are underground. So they got these gray boxes every once in a while between the house, and they'll bring a true enough cable into that thing. And then it'll come out, and then they'll break it out to the individual wires, lines that go out to the different houses. And our fusion splicer. So our fusion splicer this is our fusion splicer, this guy right here. It's in that box on the very end, but it's a single strand fusion splicer. It's very expensive, but it comes with a cleave that's about $300. So it's we'll talk about cleaving. In fact, well, not cutting. Cleaving is different. So what we do when we cleave is we're trying to get the end of the fiber. So what we're trying to do when we cleave, so when we cut, so I can cut fiber with a pair of scissors. And so that's cutting. But anytime you just cut, you're going to end up with cracks and all this kind of stuff. When we cleave, what we do is we end up with a perpendicular right across it. So we have special devices called cleavers or cleaves that generate perpendicular cuts. Well, breaks really. So cleaves don't cut, they break. So what a cleave will do is it'll scribe it, and then we automatically pull it straight out, and what it does is it causes it to break perpendicular. Does that make sense? So scribing is basically notching. And you can see, if you go to Lowe's and you buy some glass, they don't cut the glass. And they call them glass cutters, but they don't cut the glass. They're glass scriber. And then what they do is they'll take it and lay it across something, and it breaks. And it's a really good break, right? You ever seen the break people know what they're doing? So we use devices called cleaves to generate, and we have extremely expensive ones, and we got one that runs on the neighborhood of $80. So this is our small cleave right here. I can get it open. And we'll see how to use this product. So normally, if we're going to go ahead and do other work with it, like with connectors, we'll use this cleave right here.
That's the old one.
No, this is what we do when we put on connectors. We don't use a $300. Well, you could. We don't use a $300 cleave to put on a connector because you're gonna polish the end of the connector anyway. But when we do a fusion splice, then we need a very expensive cleave. So this is the cleave that comes with the This is the cleave that we use with the fusion splicer. Now I could use this to put on connectors. So this is the cleave that comes on with this. Yeah, but if I'm going to put on a connector, we're not going to use an extremely, so these guys right here,
Yeah.
We have different things we put into this slot right here that sets the length, and here's the actual cleave. I'm not going to pass this around, guys, but it's got a little cleaving wheel, if I can get it under the camera. It's right here. And this guy automatically cleaves and moves the glass that you cut off into a storage chamber right here. And it does that all in one whack. So this is the cleave that we'll use when we cleave for our fusion splice.
Oh, I thought you were going to pass around class.
So this is our fusion splice. This will run off batteries. So we have batteries to charge up. In fact, one of the battery's not in there. We have the adapter that allows it to adapt over to a regular. So this is not the battery. So we'll run it off a power supply. But what's nice about this fusion splicer is portable, so you can take it with you. So this is the actual splicing right here, and we'll look at this and see how to use that. This is a little heater, so it uses a heat shrink protector that once you put your splice, you put it on before you do your splice. You put this little sleeve on there, and then what you do is you heat shrink it down on there. You know. Huh? Yes.
Like solder.
But that thing's really slick, and it took us a long time to get it. Fortunately, we had a guy that came through the program, and he worked down at Jim Walter's mine, and they have a lot of fiber down there. And when we taught this, what he would do, he would bring his fusion splicer up to us and let us use it until we could get our own. So we've been doing it for quite a while, but with ours now. Material system, hard clad silica, and this is okay, but it's not really important for us to know. In fact, I might even take it out of the PowerPoint. Tight buffer, loose buffer, are you okay with those? And then the different type of cables. And like I said, we'll look at this chart up here. It's a lot better than so we got two types of splicing. We have mechanical splicing, and then we have fusion splicing. Your mechanical splices are subdivided into two categories, what we call a temporary splice and a permanent splice. So the mechanical splices that we have, this one is called Fiber Lock, and this is put out by 3M. This is a permanent splice, and we'll see how to put this guy on. But it's a crimp splice, so we have a special crimping tool that I didn't bring over. And once we cut it to specification, so what you have to do is we have what we call a stripping template, or a template that you use to cut off so much coating, strip the lengths precise, and then of course your jacket and everything to get it into the splice. But I don't know if y'all can see this. I'll pass it around. This is the little crimp things right here. So what happens is when you crimp this, it pushes that in. So don't push down on that. This will be one of the splices. We're not going to use this one because, like I said, these are permanent splices.
There's also ones that aren't permanent temporary splices.
Yeah, this is a temporary splice. This is the one we'll be using. This is called a universal splice. And this one's actually been used before. What I like about it is it's got a sight in it. And you can put your tester on there, your light source, and you can tell when the fiber actually comes together, which is pretty neat. And then we have some Corning. These are, I didn't bring them, or did I? We have some Corning splices also. And then, of course, Fusion splice would be the best splice. But like I said, these mechanical splices are on the average around $5, $6 a piece. And then the Fusion splicer, the splices are free, but the equipment to do the splicing is what's so expensive. But that would be the best splice that you would possibly get. And what it does, it allows you to, like I say, buy these pigtails from these companies where they've gone through the process of terminating for you. And then what you do is you fusion splice it, and you end up with an extremely good. So here's our. We have Corning on the bottom. These are twist type connectors. We got some of these. We have Fiberlock, and then also the Ultra Splice, which is the one that we'll be using. And these are splicing trays. So I brought a splicing tray in. There's a couple of splices in here. One of them's broke for some reason. But so what we do is this is going to be the weakest part of the link. So what you've done is you've got rid of all your Kevlar, you got all your jackets off there, you got all your coating off there. So what you do when you splice, you basically have stripped off all the protection for your fiber conductor. So what we do, of course, is we put these in splicing trays. So this is a splicing tray. And then what you do is you bring your cable into one side, and then you use wire ties to tie this down really, really good, right? You understand? So this is what you need to put your splices in, because like I said, you strip off every bit of the protection for your splice. And then you can see the actual protection tube that we put back on there to protect this, protect the splice itself.
There's a temporary splice. Have any way of terminate each fiber on the connector rather than temporary splices. It would have made this job.
Yeah, it would. And like I said, it's easy to do. You have to strip them to precise lengths though.
Yeah.
And that'll carry the little blue thing. If you put one with the coating on it, nothing but the coating. So if the tight jacket is stripped off, or if you're using loose buffer, then what you'd do is you'd put the little blue thing in there. See what I'm talking about? Oh, you don't have it anymore.
The little blue cap?
No, it's a little tube. So this is set for tight jacket. Oh, where'd it go? Oh, yeah. So this was lost one of them. So it's got this little blue tube right here. Yeah. So if you strip out, if you're terminating fiber that's coming out of a cable that don't have the tight jacket on it, then you would run your coating through this, and then you strip off your coating. If you're using tight jacket, if it's got a tight jacket, then you pull the little blue thing out, and then this will go out onto that 900 micron tight jacket and twist it down.
So we have something called a fan out where you take the loose tube, you cut the loose tube off, and you got all those individual fibers.
Well, then you'd have to take the blue thing off.
Yeah.
So you'd send it through the blue thing. I'm sorry.
Yeah, the fan out kit's like that blue thing where you put it through this.
And then you would clamp down on, then when you twist it together, so you see it's got these things and you twist it to lock it down. It's got a compression thing. Well, right now, if you have your tight jacket, if you leave your tight jacket on, then that's 900 microns, which is the standard size for a tight jacket. But if you come in off a breakout cable that don't have the tight jacket on, then this right here is designed to clamp down on the coating broker.
Okay.
And give you a good.
Yeah, I'm following.
And I don't know how much those cost. We get them through Fiber Instrument Sales. That's where we get most of our stuff from for fiber. Now these are your different connectors. We have ST connectors, which are the ones that we're going to put on. We have SC connectors. I'm sorry, SC. And I think we got a cable that's got SC connectors on it. So these are the ones that we're going to be putting on. These are ST connectors. So these are ST connectors. Some of them are metal. You can get metal latching mechanisms. Those cost a little more. The ones we have, of course, are plastic because they're the cheaper ones. And so some of these you'll see have metal on them. This is an SC connector. No, but LCs are basically they have the same basic layout of an SC. They're just littler.
They're smaller and they've got that.
Yeah. So that's about the only difference. But as far as terminating, they're the same because the ferrule, which is what the final thing that the thing actually goes through, they're the same size. So how you terminate them and how you put those on from scratch. Now, of course, this is a pigtail, and like I said, this is real poverty too. So you have companies that specialize will put these connectors on, and then they sell them to you as a pigtail. And then what you do is you fusion splice them, or you could mechanical splice them, but the most popular thing is to fusion splice them onto your actual cable, and then you don't have to go through the process of putting this on. Now for multi-mode, I don't know if they've got them for single mode, but they have crimp-on connect. They have quick disconnect connectors on there. So let's see what else we have here. So we have an ST, we have an FC connector. So these are usually what we use for single mode fiber. And these guys are pull proof. They screw down instead of bayoneting down. And like I said, the end alignment on these are so critical that we don't want the fiber to move around or the tip to move around. So usually, so these are the connectors we have. We have some SC connectors here, by the way. I think I brought one out. So here's the actual parts to it. And we'll look at the. But the process of putting the connectors on are basically the same. The only thing we got is the retaining mechanism there. What else do we have here? FDDI, which is Fiber Data Distributed Interface. And we used to have an FDDI cable. Here's FDDI. And what this does is you terminate both sides at the same time. Oops. Well, this is usually used for what we call a ring topology. Yeah. And this is a quick disconnect too, so it snaps in and snaps out, very, very similar to an ST connector. ST connectors, and it's basically the same feature, but here both of your cables are terminated at the same time. So one of these cables are used, one of these conductors is used for transmit, the other one's used for receive. So even though we have the ability to send light in two directions at the same time, they very seldom do that. So normally what you'll see is two cables, one for transmit, one for receive. Well, if I'm using SC or ST, then we would have two connectors, where this guy right here will just snap into the and by the way, we've got the end electronics for FDDI. And then we have a smaller version of this. Let's see if they show that on here. I don't see it. Maybe it'll be on a chart. Of course, over time, things have a tendency to get smaller. We'll have to look up there and see what this is. Oh, I believe these are two LCs. Sure are. To this, they've just been they've been snapped into a unit that makes it appear kind of like an FDDI connector. But these are two LC connectors right here.
So that's what when I went to the smelting facility, they had what looked like that, and they had ST.
Yeah, well, what this is an LC and this is an LC, but what they have is they have it snapped into a little, I don't know if you'd call it a yoke or something that runs them together. You can see it when I pass this around. It's got two ST connectors on the end. That's all the different connectors that we have available to us. And like I said, in a minute we'll go up there and so FDDI3 ST feed throughs. We can splice multiple connectors of these together, and we'll see what we're going to do with that. So this is a feed through right here. So we literally could connect multiple cables at the same time. So this is an ST. So this is the female part of an ST connector. So you can actually see the bayonet right here that the thing snaps into. Okay. So, yes, a coupler is all it is. So see, you can see. So it lines up. So it's got a key on the side right here. And so and then you look at the actual female counterpart, it's got a slot cut into it. So what you want to do is align that, and then it's spring loaded, and then you come over and snap it down. Now the problem with ST is not what we call pull proof. So you can actually see when I pull on the the name slipped off. When I pull on it, you can actually see it pull out. So that's one of the disadvantages, but it's used so much because it's a real nice quick disconnect on there. In fact, this is the same type connector that we use on oscilloscopes and a lot of our test equipment because it's real fast and gives us a pretty reliable connection. So as long as we leave enough slack on here and don't pull this tight, then this is a really good connector. So this is probably, this and the SC connector are probably the most widely used connectors out there. And I'm still missing my end cap for one. I need to put these up in fact. So we'll go over here. We'll go over here now and look at all the different connectors that's available for fiber optics. So 3 parts of a connector. We have the connector or plug, the receptacle, and the adapter. These are actually connected. So we have the ferrule. You know, ferrule. Okay, Michael. Then we have what we call the retaining nut. So what would that be? This is the ferrule. This is the retaining nut, whether it's screw or bayonet or whatever, right? You understand? We can't see this. This is the back shell. right? And then this right here is the what? The beam. Usually the back shell is covered up. The back shell is covered up by the beam. And then we have the cap, which is this. Yeah, there we can see it. This one we can see the back shell real good. So this is the ferrule. This is the retaining nut. This is the back shell. And of course, this right here is the beam. Are we okay? And this is, by the way, this was put on by one of our students. So you see the back shell. So we have a cribbing tool, and you have to strip this thing precisely, make sure everything fits right. You understand? So normally what we get is we get what we call a stripping guide or a stripping template that we can come, or we come up. That's the best way to do it, or you'll get the measurements where you'll have to measure it out. But a stripping template, you basically just set it on there and strip it according to those guides. And it's got to be right. Right? You understand? That's the problem. So we have the Kevlar and everything in here. So this is really a good connector. So these are the parts. So the ferrule, it's got an extremely small tube through there. Methods of coupling: butt, expanded beam or lens, keying. The keying prevents it from doing what? Rotation. So the BNC connector has a key on it. And then we looked at those. Technique and installation: butt coupling. Connectors are mechanically positioned close enough for the beam to pass from one fiber to the next. So what does butt coupling mean? That means you're going to butt them things up against each other, which is very, very, very popular. Expanded beam or lens coupling uses a lens system to increase the size of the beam at one connector and reduce it in the other. We don't have any of those. Everybody okay on a key? Prevents the rotation of the connector relative to the other. Contact: low signal strength loss, low reflection values. Non-contact: more reliable in environments of high vibration. So in non-contact, the ends are not touching each other; they're actually apart, right? You understand? And then they use lens mechanisms to aggregated design features that make a connector produce unique. Connectors may be made by different manufacturers by the same style are usually compatible. Connectors with different styles are not compatible. Sometimes an adapter is available so you can go from one to the other. Are we okay? So these, we're looking at different types. So one key, typical loss is 1 dB per pair. This is 0.31 dB per pair. And this is just typical. So we understand dB now, right? Everybody okay? Yeah. Loss, contact, and non-contact, connector types. I don't know what that is. So this is ST. People call it Sarah Tango. What do we call that alphabet? Use that in the military all the time. Phonetic. Phonetic alphabet. This is the most used. It's a bayonet canine. It's key. Physically contact connector. Not pull-proof or wiggle-proof. The low average is between 0.3 and 0.5 dB per pair. So that means per pair, right? Don't understand what that means. Sierra Charlie, this is the second most used. Snapped on and snapped off, key, physical contact connector, full and wiggle proof. Low average cost per pair is 0.3 dB per pair, and it's a higher cost than the SD.
We usually call staff.
So this is ST connectors, and these are the ones that we're going to be putting on. Everybody okay?
Yeah.
In 3 parts, we've already looked at that when we're up here. We'll strip that down. And then this has a ruler out there that you can look at. SM connector, this is SMA. We can look at that. It's non-keyed, non-contact, moderate average loss, 1 dB per pair, moderate cost, but it's pull-proof and wiggle-proof. Y'all understand those terms? Pull-proof and wiggle-proof.
Foolproof, you can't pull it out. Wiggle-proof means it doesn't wiggle out with vibration.
Yeah. So wiggle would be this, right? You understand? And then pull would be what?
Like someone tripping over it or something.
Are you making the cables too tight?
Yeah.
And not leave any slack. Even if you run the cables the exact length, it's going to have problems because just with things expanding and contracting with temperature and heat, everything. Yeah. So sometimes it might work and sometimes it might not work. Just simply because just with temperature. So we always leave slack. In fact, most of these rooms you go in there, they'll have a loop in the cable. Biconic, non-keyed, non-contact, moderate loss, cost. It's not foolproof. FDDI. This is a dual fiber keyed, physical contact, moderate loss, and cost. Both pull-proof and wiggle-proof. So this is a mini BNC, which we don't have. This is FDDI. And then SCON. These are just different characteristics of these different types of things. And, so what's the average loss? But the ones we're doing, so what's our average loss per pair for ST connectors? I wish it was what? For ST connectors? No, better than that. 0.3 to 0.5. Huh? Yeah. 0.3 to 0.5. Of course, what we shoot for is what? 0.3, right?
Yeah.
Y'all take y'all's when y'all term it down with a power meter? A power meter.
The one that they assigned me, which is very irritating, is that it will check the reflectance, and then it'll check EV points. And if it's not within I think like a 0.25 loss, it won't pass it. And if it's reflectance is like it might be. I think it's actually
Refractance is when it passes into the clad.
Yeah, I think that was that.
In signal mode, you do have conduction through the cladding, but it's going to be very, very low.
Yeah. But it has to be within negative 25 or 35 dB for refractance. And then it's got to be 0.25 dB for better. Or else we can't certify it.
Steps for technique. Gather the necessary tools, supplies, install the booth. So that's very, very so you do all this work and you forgot to put the boot on.
Cut it out.
Install the boot, prepare the cable in, attach the connector to the fiber, inject the epoxy or adhesive connector with preloaded with hot melt adhesive. So you can buy these connectors that already have the epoxy in there.
Yeah, I asked Ross about that last night. But for me, one, it wouldn't go in all the way, and pull back.
Attach the connector to the cable, mechanical foot grip, or what we're talking about is there's going to be a crimp tube. So part of the back shell is a crimp tube. And we have different types. Sometimes the crimp tube comes out separate. Our crimp tube, the ones we got are fairly cheap connectors for obvious reasons. So this back shell, this is the crimp tube right here. So what you got to do is you got to remember you'll put your boot on first. I'm sorry. You put the boot on first, then this is the crimp tube. You got to put that on there first, right? You understand? And then you'll crimp the cable. Then you have a crimping tool that we crimp this down with. And we don't use the one that we use for copper. So it actually crimps, I guess in a hexagon or so it crimps on all fours. Yeah, you can see this one. This one was crimped with our crimp tool right here.
And it's mainly to secure it, not to secure the fiber itself. Try to secure the fiber itself so we can weight when you have pop.
Yeah, the epoxy and there's a technique to that too, which will.
So if you were to compare it to the crimp plug that we have, the epoxy is like the first one.
Yes. So epoxy cured in an oven, adhesive. This is what we're going to use. We have an adhesive and we have an accelerator. Hot curer epoxy is already in the mixer. And then you have mechanical force, polymer grip, and chuck. These kinds that grip are attaching the strength member. We're either going to crimp it or epoxy it. We're going to crimp ours. Polishing, brazing the end with polish on paper, films, or paste. Cleaving, scribing with a cleave perpendicular to the conductor and breaking evenly. So we looked at the cleave. Y'all don't have to use the cleave.
We do, it's a different kind. That's the older model we used to use. We've got one where you hold two buttons on the side. It opens up the whole cleave. You slide the fiber in where you can see it on the top. Press a button on top of it. It cleaves it. If you press one button, pull out the fiber, you have to move on. Pull out the
Okay.
So it basically cuts the exact length you need it.
Well, on this one you have to line it up, but on our cleave that comes with the fusion splicer, we have a special little thing that you put in there that cleave.
Yeah.
That you cleave it to the right length.
Yeah, that's essentially what we have. So we've got.
And then we got another one we put on there that's got the scale on it that we can cleave it to any length we want to. This one though, what you have to do is you
See, I could probably grab one of the bags that has a perfect mechanism for that. That has that leading through and the other.
yeah, but this guy here is still around $80, and it don't look like it's much to it. But
Not really, I probably could put that out.
I don't know that you could print the mechanism out, but the actual little thing right there that cleaves it.
Like leading blade.
Yeah, it's the one that's probably what's very, very expensive.
Yeah.
And we'll look at this one now. Of course, you're going to have to dispose of the cleave glass out of it. But everything clamps down, and we'll show you how to use this guy. So yours probably costs a little more. We probably wouldn't be able to.
The termination kit that you get is around $2,000. That's with a crimping mechanism that has a laser that feeds through the connector and tells you whether or not you get a good termination or bad termination. So you can kind of insert it and it shows up green and when you're good, you crimp down on it, it shows red, you gotta pull it out and insert it.
Oh, wow. And what's the cost for the connector?
also they're like $2 each.
Maximum loss per pair, dB per pair, everybody okay on that? So maximum loss when connectors are installed correctly. Average loss per pair, and this is typical loss. Repeatability of loss, maximum change in dB pair. Everybody okay there? Reflectance is what you said. Reflection of light in the connector back toward the light source. So this would be dealing with how perpendicular your cut was. Does that make sense?
Yeah. I think it was practice.
So splice termination reflection is bad. So if we get a good if we got these butt connectors, then this is the kind of problem we have. Over sanding, you get this loop. Sanding at an angle, you get this loop. Right? You understand?
Yeah.
Wavelength in nanometers, spectral width in nanometers, numerical aperture, spot size in microns. Everybody okay with that? So we talked about these different things. So when we use our power meters, we're going to have to know the wavelength of the cable that we're dealing with. Because one of the things you're going to do on your light source is you're going to specify the wavelength of the light that is transmitted. So if you use the wrong wavelength and what the cable is designed for, it's going to give you erroneous readings. Optical power budget, the maximum loss of optical spring that the transmitter receiver can withstand will still function at specified level of receive. Can withstand. Will, it looks like some words are missing out. Don't it? It will still withstand and will still function at the specified level of accuracy. That looks a little better, doesn't it? So this is typical optical power budgets. So I think our wavelength on our 62.5, this is what we use, 62.5. The optical power budget over the whole system is 16 dB. So that's what we use. 1300, these are usually, when we get into a single mode cable, we run at a lower frequency. Okay? Yes, no?
Yeah. Oh, it was reflecting.
Yeah, that's what I thought. Okay, guys, y'all go ahead and take a break, and we'll start looking at our labs.
Yeah, I kept getting like a 16 to like 24 dB loss on my connections.
That sounds like a lot.
Yeah, I can figure out what was going on.
So what was going on?
What my boss had used everything, he said half of the connections were faulty. And that's what happens. When you get connected yourself to that. So the other half is probably the UTR set up right or not.
You have to zero it out, right?
Yeah,
So what we do on ours is we have a reference cable.
Yeah, we use launch tails, that's called. And you do a compensation. So you hook up the launch to the OTDR and you've got a couple of it hooks the tail up to the launch. And you do a compensation. And then it gives you the width of each cable and then it gives you the quality.
Yeah, that's we can't afford those.
So
So ours is just power meters.
yeah, so then you can kind of zero out those and then you hook up the launch to one end connector. And then you go on the opposite end of the fiber and the tail and you can get the exact length of the fiber. We were dealing with fibers that was, I think it was 2,000 feet long.
Oh, Yeah, me too.
curious if you get all our lecture knocked out and you get all of the lab knocked out. Yeah, 4 days left.
Yeah. Not much time, you're right. You didn't show up for class yesterday. So what we're going to do, we got a couple labs that we'll look at. And one thing is we're going to allow y'all to strip a conductor to a precise length. What you have to understand is when you do this stripping, to be able to put this in a splice or inside a end connector, your stripping lengths have to be fairly precise, right? Everybody understand that? Now, we're going to be working with a very, very small piece of fiber. I think what you're going to do is 6 inches. And the problem is when you start dealing with this, and, I need to put these up pretty fast, is that when you start dealing with this in a real small length, then what happens is everything, while you're doing your stripping, everything wants to move inside the cable. Okay. So what we're going to do, and you'll never do this in real life, is when you get yours, you're going to take one end and tie it in a wad. Knot. Now, we're not going to do that in real life, but what that's going to do, it's going to allow us to work on this other end and strip it according to the specifications that we need. I think I need to go get one, a little permanent marker y'all can use. So, of course, what we have here is the outside jacket. And this is 62.5, 125. So the way these things are specified, by the way, I think we've already talked about this. The first number is they give you the size of the core, and then the second they give you the size of the cladding. So 62.5, 125 would be 62.5 micron core, and 125 would be 125 micron cladding. And then the coating comes out a pretty good deal too. I need to get those. So when we strip these things, I'm not going to do it to a length. We would come up here and we would put it on a tape measure or whatever. If I got a template right, you understand. And normally what we do is we want to work against a dark background because it makes it real easy to see fiber. So we have mats over here that we use in fiber optics. Has these black things on the back, but these tables right here work really well too. And then of course, what we do is this is a 3-hole stripping tool. And what this thing here does, it does everything we need to do. It does the outside jacket except the Kevlar. It does the tight buffer, and then it does the coating. So what we do is we'll just take this, and what you want to do is you don't want to pull this off with the stripper. What you want to do is just cut it and then take it off, and then notice I twisted it and broke it, and you need to pull this off with your hand. I understand that.
Kevlar.
Then we have Kevlar. Now you can't cut Kevlar. You have to have special scissors. They're Kevlar scissors. These are real cheap ones, by the way. They could be very, very expensive. We got a expensive. Now what we normally do to keep it from fanning out, can you see what I'm doing? I'm twisting it together. And this way it helps it fan out. And then we'll mark this to the right length. So your Kevlar's got to be a certain length too. And then what you're going to do with this is we're going to cut this right with our Kevlar scissors. to a certain length. And we got some bags over there, right? You understand? Everybody okay so far? And then according to the specifications, once we got a Kevlar strip, then we'll strip off the tight buffer. We come back to our tool. And so the outside hole, the biggest hole, this is for the outside jacket. The next hole, the next little slot is for the tight buffer. So we'll take that. Now what we're going to do is if you got to strip off a lot, we want to come in here and we want to strip it off at about a 1/4 inch length until we get down to where we want to get. Everybody understand that? So if I'm going to strip off an inch, I don't want to try to strip off an inch. We'll do it at a 1/4 inch at a time. I should have on my safety glasses, guys. Y'all can write that.
Yeah, we're gonna write you up.
Okay. All right. Then the next thing we're going to do is we're going to strip off the wad. We're going to strip off the coating.
Yeah.
Okay. So we'll come up here and put that in the last slot. Be real careful because you're down to the glass now. And if you don't line it up inside these D's right here, then you're going to cut it. Right? So we'll come up here, make sure we line up in the slot, and we'll cut off the coating. Now what you're going to have to do on this one, if I can get it, which way do I need to go? This way. No.
Further out.
Okay. Notice I've got my stripper at an angle. See that?
Yeah. And
then we'll come up here and we'll strip off the coating, and then we'll clean it, and usually it'll take a couple of times to get all the coating off. And then I'm down to the fiber. And the last thing we'll do is we'll get a alcohol wipe, and we'll wipe it off. We don't want to use our fingers, especially when you go into your epoxy. You want to make sure the last thing you do before you epoxy it into your connector is you clean that with an alcohol wipe. Right? You lay it in it, you beat it over, and then you pull it out. And what you'll hear is once it's clean, you'll hear a squeak. Here it goes. It's kind of like your hair when you take a shower, pull it through there, it squeaks at you. Well, you're going to get the same thing with the alcohol wipe. It means you put enough friction on it. It means it's clean too, because it won't squeak. For some reason, it won't squeak against the coating. It'll squeak against the glass. So when you hear that squeak, it pretty much means. So this is what we're going to do first, and y'all understand we're not going to do this in real life. The only thing we're doing it for is to what? Keep all this stuff from pulling out. So if I come over here and pull that Kevlar, it'll pull right out of there. And you're only dealing with a 6-inch piece of this. And the Kevlar's pulled out a little bit, so notice this one's got I can't see the Kevlar in there even when I cut it. So I would probably tie this one in. Get it close to the end as you possibly can, and then cut this until you can see both the Kevlar and the conductor before you start making your cuts. Right? That makes sense? Are you okay? Yes, no?
Yes.
Next thing we'll do is we're going to measure one of these real long cables. Can't use this. We probably need to clean these off. We got some pretty long cables. I think we're going to do two. So when you do your DV loss or you're measuring using the power meters, is these cables have numbers on them. This is a fairly short cable. And I'll go get the alcohol wipes too. So what you want to do on these, even though it's got these end caps on there, you need to, before you put it in your power meter, you want to do what? Clean it off real good, right? And then the second lab we'll do is with our power meter. We got a new power meter over there. It's never been used. We got the older power meter. But you're going to do this as a team.